I'm Mike Abbott, a flight instructor, and your host for this edition of Flightline, Teaching Flight Safety. As flight instructors, we often champion the safety of flight to our students, but when was the last time we stopped and asked ourselves, just how safe is flying? Or, a better question may be, is flying really as safe as it can be? Until recently, accident statistics indicated that flying was becoming safer. In fact, NTSB reports reflected a decrease in the general aviation accident rate from 1984 through 1990. However, in 1991, the accident rate began to rise and continued to increase through 1994, even as flight activity declined. More significant than the statistics are the events which led to the accidents. An investigation into the causes of accidents and incidents can enhance flight safety by helping us identify risks and recognize hazardous situations. This knowledge can be passed on to our students to prevent accidents in the future. To explore this idea, we'll profile 3 examples of general aviation accidents. After uncovering the circumstances surrounding each accident, we'll use the lessons we learned to formulate teaching methods that we can use to help our students avoid making the same mistakes.
Pilots at Lakeford Airport rarely encounter much traffic or trouble, but on one hot July afternoon, this small uncontrolled field became the site of an unfortunate accident. A Cessna 172 crashed into trees during initial climb after departing runway 17. The pilot and 1 passenger suffered minor injuries, and 2 passengers were seriously injured. The airplane was destroyed. There was no evidence of prior damage to the airplane or of any equipment or structural failure prior to impact. The first step of my investigation was to track down information about the airport and runway environment. The field elevation of Lakeford Airport is 1,000 feet. Runway 1735 is a grass strip 2,100 feet in length, with trees located at the departure end of runway 17. Next, I spoke to a pilot who witnessed the accident.
I remember thinking that the 172 was taking off in a slight tailwind. It was only about 5 knots, but it hadn't been steady coming from any one direction all afternoon, and it was a pretty hot day.
How hot do you think it was that day?
Well, see, it was about 3 o'clock in the afternoon. It must have been 95 degrees. That's typical for July around here. I saw the airplane take off, and he just barely made it off the strip. He lifted off like right over there. I mean, he was almost in the weeds. He was level in ground effect and just barely started to climb. I didn't think he was going to clear those trees. Sure enough, he didn't make it.
It appears as if the 172's performance was insufficient to complete the takeoff roll on the available runway and clear the trees after departure. Although the pilot, Bob, refused to comment, I was fortunate to interview one of the passengers who was on board the airplane the day of the accident.
Well, I recently moved to Lakeford. I had asked Bob to come visit me, so I took some friends out to the airport to meet him, and he offered to take us up over town.
How many passengers were there?
There was 3 of us plus Bob.
Was there any baggage on board the airplane?
Well, Bob was planning to stay overnight, so he had a suitcase and his flight bag.
How much would you estimate that the 4 of you plus that baggage weighed?
Well, I'm about 165. Bob's the same. Gary is about 180, and Jim has to be about 200 pounds. The baggage couldn't have been over 25 pounds total.
Do you remember if you had full fuel that day?
Yeah, Bob had asked the guy to top the tanks off before we left.
I calculated the airplane's weight and balance based on the information provided by the passenger. According to my figures, on the afternoon of the accident, the 172 was 35 pounds over the maximum takeoff weight limitation, and the center of gravity was located near the aft limit. Were you aware that at the time of the flight, the airplane was 35 pounds overweight?
No, I had no idea.
Do you remember Bob performing any calculations prior to the flight? Did he get out the airplane flight manual?
None that I'm aware of. I don't think he even knew we were going to go up until we're all out looking at the plane, and then Jim had asked him.
The takeoff distance chart provided additional clues as to the cause of the accident. At a maximum weight of 2,400 pounds and a temperature of 95 degrees Fahrenheit, 35 degrees Celsius, I calculated the 172's ground roll to be approximately 1,625 feet. The total distance to clear a 50-foot obstacle equates to 2,809 feet. To arrive at these figures, I increased the distances by the percentages indicated in the performance chart notes for operation on a dry grass runway with a 5-knot tailwind. Was Bob's experience as a pilot a factor in his decision to fly that day? Logbook entries indicated that Bob had approximately 200 hours. A month before the accident, he completed a flight review at his local airport. But the majority of Bob's flights were in the local area, and he had never flown to Lakeford Airport before the day of the accident.
Let's examine this all-too-common scenario. In a study of NTSB accident reports over a 6-year period, it was determined that pilot error and poor decision-making accounted for nearly 77% of all accidents. For example, numerous takeoff accidents involved attempting overgross takeoffs, failing to account for high temperature and density altitude effects, or failing to abort a takeoff. A lack of pilot understanding regarding operations with varying field conditions, runway lengths, and elevation and temperature effects was indicated as a cause in many of the accident reports. Let's examine how a combination of these factors played a part in Bob's accident, and how we can teach our students to avoid these same errors. An overgross takeoff was attempted. Operating in excess of maximum certificated takeoff weight results in a longer takeoff roll, reduced climb performance, and an increase in stall speed. There was a failure to account for high temperature and density altitude effects. It's a mistake to assume that because terrain is relatively low, density altitude does not need to be considered. Regardless of the field elevation, an increase in density altitude still results in an increase in takeoff distance, a reduced rate of climb, an increase in true airspeed on approach and landing, and increased landing roll distance. These factors, combined with a short runway, can lead to disaster. Students should be taught to make a practice of calculating weight and balance and determining airplane performance during pre-flight preparation. In addition, it's essential that students learn to use the information obtained from performance charts and graphs effectively. For example, adding at least 50% to all takeoff and landing distances can account for pilot technique, underinflated tires, dragging brakes, weak engine, or any additional variables which may affect optimum performance. It's important for students to understand that data obtained from these charts is based on a properly tuned airplane in good condition with solid brakes and the assumption that the pilot has average piloting abilities. In addition, performance figures are based on a specific procedure, aircraft configuration, and airspeed. For example, takeoff distances are normally predicated on short field techniques, and maximum rate of climb charts are based on operation at a specific indicated airspeed. What led to this pilot's downfall? Attempting an overgross takeoff from a short grass runway on a hot day with a tailwind. Why would a pilot ignore all these factors which have such a tremendous effect on the safe outcome of the flight? The answer might lie in the pilot's past experience. Flights in familiar surroundings can become routine, and complacency may set in. When faced with an unfamiliar environment, some pilots may not fully consider all the variables which affect the flight. As flight instructors, are we providing sufficient training to prepare our students for the wide variety of situations which may be encountered in future flights? A study of NTSB accident reports suggests that maybe we are not. A conclusion which can be drawn from many accidents which occur during instructional flights is that CFIs may fail to effectively teach aircraft operation in other than normal situations. Numerous accidents with both instructor and student on board involved operation during hot weather, short runway use, soft field use, operation in excessive gusts and crosswinds, improper fuel tank switching after a power loss, and loss of control following an inadvertent door opening. During training, we must expose our students to a wide variety of flying environments and abnormal situations. If it is not practical to operate at many different airports, we can present flight planning scenarios which involve a variety of field conditions, runway lengths, and varying flight conditions such as temperature and wind. We can also discuss accident reports, such as the one we have just investigated, to provide a vivid example of situations to avoid and the importance of making good decisions when presented with an unfamiliar environment. These ideas must also be reinforced during flight reviews and advanced training. Generally, accidents are not caused by just one, but a series of events. Although Bob made many poor decisions prior to takeoff, another significant factor was Bob's failure to reject the takeoff as soon as it was clear insufficient runway remained and aircraft performance was inadequate. Pilots can easily develop the mindset that, once initiated, a takeoff or landing must be completed regardless of the circumstances. Go-arounds are often discussed and repeatedly practiced throughout flight training. However, a procedure that may be overlooked is the aborted takeoff. Students may feel committed to a takeoff once full power is applied and the airplane begins to accelerate. It should be clear to the student that an option to discontinue the takeoff always exists if a problem occurs. A check of the engine instruments to verify that the engine is developing full power and is operating within limits should be made during every takeoff. Slow acceleration or any hesitation of power is sufficient reason to reject the takeoff. If aircraft handling is difficult, loss of directional control occurs, or insufficient runway remains to complete the takeoff roll, students should be conditioned to discontinue the takeoff. Statistics indicate a lack of sufficient training regarding rejected takeoffs. The NTSB cited failure to abort a takeoff or a delayed abort in the causes of 229 accidents over a 6-year period.
For general aviation pilots operating at busy airports like this one, wake vortex encounters can be a very real concern and, as revealed in our next investigation, can lead to accidents. The pilot of a Piper Archer was on final approach for runway 33. The airplane crashed just short of the threshold, swerved to the northeast, and came to rest on the approach end of runway 36. The pilot suffered minor injuries, but the aircraft received substantial damage. I spoke to the pilot about what he experienced when the accident occurred.
Well, it's an experience I won't soon forget. I was told to proceed direct to runway 33 and pass behind a Boeing that was on final to 36. When I was on final, the plane rolled violently to the right, and I added left rudder and full left aileron to try to get it level again. Well, I thought I was going to stall, so I nosed it down, and that was a mistake because that ground was rushing up so fast I pulled back hard, but by that time it was too late.
After reviewing the airport diagram, I learned that the approach ends of runway 33 and 36 are approximately 560 feet apart. Radar data obtained from ATC indicated that the Archer was at an altitude of less than 100 feet AGL when it crossed the flight path of a Boeing 757 on approach to runway 36. The 757 had passed the crossing position of the flight paths approximately 30 seconds prior to the Archer. Trends in the radar data indicated that the flight path of the Archer was slightly above the path of the 757 at the point of crossing. The details of this accident suggest that the Archer encountered the Boeing 757's wake vortex. But if the Archer was above the Boeing's flight path, how could this occur? To find the answer, it was necessary to take a closer look at wake vortices. The vortex is a mass of rotating air which consists of a core and a flow field about the core. The size and strength of the flow field determine the risk posed to the trailing airplane. Research indicates that the characteristics of wake vortices are more complicated than many pilots realize. In addition to the aircraft's weight, speed, and configuration, the strength of the wake vortex is dependent on wing shape and angle of attack. Atmospheric conditions also play a very important role in determining the strength of wake vortices. Atmospheric stability, winds, ground effect, and turbulence are significant factors often overlooked when discussing wake turbulence. For example, the movement of wake vortices near the ground has been observed to be quite complex. Wake vortices tend to remain in ground effect and spread outward at a speed of 3 to 5 knots plus the wind component. In the case of our profiled accident, the left vortex of the 757 typically would have extended 200 to 300 feet toward the west in ground effect. The vortex core may have been located approximately 75 feet above the ground, although research has indicated that a vortex has the potential to bounce twice as high as its steady-state height. In addition, the diameter of the vortex's flow field is usually about equal to the generating airplane's wingspan. The Archer could have been affected by the vortex between the ground and approximately 200 feet AGL. Although the Archer was above the flight path of the 757, the pilot did not adequately compensate for the height of the wake vortex.
Our students should be aware of the unique movement of wake vortices near the ground, and that additional research is being conducted to learn more about these vortex characteristics. By remaining several hundred feet above the preceding airplane's flight path, wake vortices which may rise in ground effect can be avoided. In addition to vortex movement, the duration of wake vortices also is affected by atmospheric conditions. Small amounts of turbulence may significantly enhance wake vortex decay, while very low turbulence levels under certain atmospheric states can slow vortex dissipation. Even under unstable conditions, vortices can maintain high velocities for over 60 seconds. Once decay begins, vortices dissipate rapidly, but a vortex can retain almost 90% of its original strength up to 85% of its lifetime. Additional insight into the complexity of wake vortex movement can be gained by examining reports of wake turbulence encounters. Unfortunately, there's a lack of extensive data in the United States, since pilots aren't required to report wake vortex encounters. Some information is available from wake turbulence accident and incident reports filed through the Aviation Safety Reporting System, or ASRS. However, these reports may not be representative, since they're voluntarily submitted, and not all pilots and controllers may be aware of the ASRS or are equally willing to file reports. Despite the limitations of this data, the reports do suggest that pilots are continuing to encounter wake vortices at an unacceptable rate. Many pilots involved in accidents had been given wake vortex precautions by ATC, yet took no action, either ignoring the warning or mistakenly believing that their flight path was above the vortex. While ATC is required to apply a specified minimum separation for aircraft operating behind heavy jets and certain large aircraft types, it is ultimately the pilot's responsibility to visualize and avoid vortices in VFR conditions. Airplane separation distances for wake vortex avoidance are based solely on weight, although other design features can affect the vortex formation. For example, Boeing 757 flaps are continuous from the fuselage to the ailerons, a design which researchers believe is more conducive to uniform development of the wake vortex. Research is continuing on wake vortex generation and methods pilots and air traffic controllers can use to enhance avoidance procedures. For example, the development of techniques which pilots can use to determine relative flight paths and separation distances is being explored. During certification, determination of an airplane's wake vortex characteristics by flight test or other suitable means is another step to improve safety. To assist in further research involving the hazards of wake turbulence, we can submit and encourage our students to submit ASRS reports providing details of any wake turbulence encounter. Wake turbulence avoidance should be a part of all levels of training, including instrument instruction and flight reviews. Many of the pilots involved in wake vortex accidents had instrument ratings. The private pilot and commercial pilot practical test standards include wake turbulence avoidance as an objective under the task of traffic patterns. Also, the PTS introductory material directs examiners to place emphasis on those aircraft operations most critical to flight safety, including wake turbulence avoidance. In addition to ground discussions, we should set an example for our students by always following wake turbulence avoidance procedures.
How important are written checklists to flight safety? Our next accident profile may provide an answer to this question. During initial climb, a Cessna 152 stalled and crashed approximately 500 yards from the departure end of runway 10. The airplane was destroyed and both occupants were killed. Investigators found that the flap indicator was set at 30 degrees and the airplane's flap surfaces were at 30 degrees on impact. No pre-impact defects or failures were discovered. To learn more about the cause of the accident, I spoke to a flight instructor who witnessed the crash.
Well, as you know, it was a 152 on takeoff, and it appeared that the 152 had full flaps down. And as you can see off the departure end of the runway here, the terrain starts to rise, quite rapidly. Well, the aircraft started on the takeoff roll and got up into ground effect and established a pretty high, nose attitude, and looked like it just was unable to climb out of the ground effect. Well, it got near the end of the runway and appeared to enter a slight left turn to avoid the rising terrain, and the nose just broke down and pitched down violently, and the aircraft struck the ground.
Would there be any reason to take off with full flaps extended?
Not in a 152, no. And in fact, the manual specifically states that full flap takeoffs are not approved.
Based on your experience as an instructor, why do you think the pilot attempted to take off with full flaps?
Well, I don't think the pilot intentionally tried to take off with full flaps. I think it was probably more of a mistake. They were left down after the pre-flight. Probably was in a bit of a hurry during the takeoff and during his run-up, and maybe inadvertently missed that step on his checklist.
I checked the airplane flight manual and found that 2 checklists to be followed prior to a normal takeoff indicate that flaps should be set at 0 or 10 degrees. In addition, the short field takeoff checklist indicates a 10-degree flap deflection. How common are accidents caused by either disuse or misuse of checklists? According to NTSB records, during a 4.5-year period from 1988 through 1993, there were 87 accidents in which checklist problems were specifically attributed as a cause or factor. 43 accidents occurred during the approach and landing phase of flight, while 35 occurred during takeoff. Landing gear was indicated in 36 accidents, fuel systems in 28, and flaps were involved in 11 of the reports. The most serious accidents involving misuse of checklists occurred when flaps were improperly configured, usually during takeoff. Pilots admitted that checklists were not used at all in 33 of the 87 accidents, while in most of the others, portions of the checklists were either skipped or forgotten. In 44 cases, a distraction drew the pilot's attention away from the problem which caused the accident. Checklist disuse or misuse may be far more widespread than this data indicates. Although checklist problems were specifically cited in these reports, accidents which were attributed to other causes may have involved some failure to properly use checklists. Accidents with reported causes such as carburetor heat, emergency procedures, fuel tank selector position, or gear extension may have been prevented by proper use of checklists.
We should set an example for our students by using checklists throughout all phases of training. This can be especially important during advanced instruction. As proficiency is gained, some pilots may feel that checklists are no longer necessary. In fact, the exact opposite may be true. As experience is gained, pilots typically fly increasingly complex airplanes, and operating procedures become more extensive. In addition, the tendency to fall back on old habit patterns or become complacent can be hazardous for high-time pilots operating a wide variety of airplanes. The fact that checklists are not used for all phases of flight is one of the most common safety problems involving checklist misuse. Typically, pilots may stop referring to the pre-flight, cruise, and approach portions of the checklist first, followed by the before landing and after landing checklists. Many pilots feel that it is sufficient to have checklist items memorized. These individuals can cite the hundreds of incident-free hours which they have flown without using the written checklists. We can remind our students that most checklist accidents involve some form of distraction or disruption of normal flight routine. When a distraction occurs while using a written checklist, it is easy to resume the checklist by starting with the last item completed. A mental checklist only makes it more likely that an item will be forgotten after a disruption of flight routine occurs. In some cases, it takes only one forgotten item to lead to an accident. Some emergency procedures require the checklist or a portion of it to be memorized. In some situations, the use of the checklist while accomplishing the procedure would be unsafe or unfeasible, especially in single pilot operations. In these cases, the checklist should be reviewed after the procedure has been performed to ensure that all items were accomplished. The additional stress of an emergency situation can lead to a critical item being overlooked. The FAA emphasizes written checklist use, and during practical tests, applicants are evaluated on the use of the prescribed aircraft checklists. The importance of following written checklists is graphically illustrated by 3 air carrier accidents which resulted in part from the crew's failure to properly deploy flaps prior to takeoff. The accidents resulted in multiple fatalities and the aircraft were destroyed. These tragic accidents serve as a reminder of how important our role is in teaching flight safety. The habits and attitudes our students develop today may shape the future of aviation. And although flying may never be 100% safe, we should do our part to help increase the odds.